Well, good morning. So the second midterm was not as good as the first midterm by simply comparing the statistics that you can see. The first midterm, the average was 80. The second one, the average was 65. But the spread was larger too. The standard deviation in the first one was 14. The second one was 20. Okay. So the second one, I deliberately made it harder. I think I told you about that because I really want to see who gets almost everything that we have seen in this class. And if you look at the distribution, I'm quite comfortable with the distribution because those are, the green ones are above one standard deviation from the mean. And that number would be appropriate for the number of A's that I plan to give in this course at the end. Of course, if the standard deviation is very narrow, that tells that the class is very homogeneous. That is, everybody is getting what I want you to get at. So from the second midterm exam, I do have a sense of where the difficulties are, but I guess I'm not sure how we can address it in the short time that we have left. A few days ago, I think I was watching a discussion Charlie Rose at the Stanford University organized it. How many of you have heard of or used Khan Academy? A few, not many. Okay, that's going to be kind of the future of how education is, I guess, reformed in some sense. It's a pretty revolutionary thing that he's doing, I think, and in part I'm inspired by his when I record my lectures and put it on YouTube. And I do get correspondence from students far, far away. But one of the points that he was making in the conversation discussion is the current system, and I think that is a very legitimate point, the current system keeps the residence time of students a constant and the amount that you learn as a variable. Okay, so you stay there for one term, and whatever you can learn in one term is all that you get from each course. And some students get quite a bit of it from such a course, and some students don't get all that they should get, but we still push them to the next course. Okay, you're done with this course, go to the next course. And so at the end of it, we have students who have learned everything that they need to learn as engineers. There are students who have been exposed but not really learned everything that they must learn in a very sound way. And those in the green, for example, I would feel very comfortable that they are doing very well. They have learned all the concepts that we have talked about in this course. And the B's are also pretty good. I would like to give a large section of B and minimize C's and D's. So this distribution actually is naturally arrived at what I'm comfortable with. The number of C's, there I think we are failing. It may be due to number of factors, but you need to put some effort. You need to tell me what I can do to help your learning. Now, if we make the time variable and the learning constant, then you can say, okay, these guys should take 2 more months of this course and work on more problems so that they bring up their proficiency to another level. And so everybody will graduate with an A, with the adequate knowledge that you need, but at different times. Okay. So one of the purposes of my second midterm, if you notice, some of you mentioned this, and I think they observed it, it was long. Okay. And it is deliberately designed to be long. Okay. If I make the exam short and easy, everybody will get A. And that means I'm testing you on lower level concepts and everybody gets it. And that was the first midterm exam. The second midterm exam is designed deliberately to sort out the A's and the B's. That means I am not only constraining it on higher level concepts, but also on time. So those who can finish it quickly and get all of that. And there are students who got 90s in this one as well. Okay. So I don't think it's an unfair exam, but it's an exam that does the purpose of pointing out to me and to you where the deficiencies are and what you should do to improve that. Now, because the average in this one is low, what I'm going to do is to bring up the average. I'm going to make this exam also an assignment. So the next assignment, assignment number 7, will be the exam. So I won't post the solution yet. Okay. And what I want you to do is not only do the thing, you can use Matlab, you can use whatever tools that you want, do all the problems, plus the last problem, you actually do the Newton method, implement, write the function, write the Jacobian. You've already done it for the linear problem. This is a nonlinear problem. So there is a learning opportunity by persisting on that. Okay, whereas if you give it up on that and then move on to the next one, we lose that opportunity. So I'm going to post that as your next assignment. I will reform it and redirect the instructions so that you know clearly what you need to do. Any questions for me on the? Yeah. Any program that you want to do? Yeah. What do you mean by that? Yeah. I'm sorry, did I not make this clear? I'm using Matlab in this course and I'm trying to teach you, but if you are familiar and comfortable with any other language, that's perfectly fine to do all your assignments as well. Okay. Any other questions? Any comments on the exam from your point of view? Okay. So in the last lecture, where is the lecture notes? We looked at numerical differentiation, what it is, how to take the derivatives from a tabulated data. Derivatives are rates of change of variables, right? And if you have a function, we have a definition for the rate of change through the limit process. And you know how to take analytically the derivatives and the integrals of the functions. And Mathematica is a very good tool for you to be able to deal with analytical expressions. Matlab also has a very similar tool called Symbolic Toolbox with a graphical user interface called MuPad, which we introduced. A lot of these things I'm just kind of making you aware that MuPad exists and what is MuPad. But because we don't have the time to go into detail, we're not exploring completely what MuPad can do. But you should be able to use that during your assignments on your own. And if you're given a tabular set of data, then we have the need also to take this rate of change of that variable with respect to the independent variable. So we went through the process of constructing the functional approximations and taking the derivatives from those functional approximations. And we derived a series of formula for example, the first derivative. First derivative at a reference point that is identified by either x1 or x2, and using only discrete points on either side that are uniformly spaced. Okay, so you should understand what these formula mean and how to use that, and we will do an example of this today. Okay, and we also saw how to derive them from a Taylor series expansion, and then we moved into numerical integration. Numerical integration is finding the area under the curve in some sense for a tabulated data. So analytically, this is the problem that we want to do. Okay, find the integral of some function f of x between a to b, certain limits, a definite integral. But we saw trapezoidal rule as the average of the function between two neighboring points multiplied by the distance between those 2 points. That's the area of the rectangle. And then you sum that up. So you take your domain a to b, divide that into a large number of small elements, and each trapezoid you calculate the area according to this formula and then sum it all up. That will give you the total area. And we talked about this difference between a local and a global truncation error. And that we obtained by using either the Taylor series or the Newton forward formula, for example. So by truncating a Newton forward polynomial with one term, a linear approximation, we got the trapezoidal rule. That has a truncation error of order h cubed. Okay, the local truncation error of order h cubed. But when you are adding them up, the error in each step accumulates. So the summation makes the global truncation error one order less. So the trapezoidal rule has a local truncation error of order h cubed and a global truncation error of order h squared. So you should understand and be able to explain the meaning of such concepts. Okay. Now we are going to look at the next formula, which is called the Simpson's rule. We started it, but I just want to complete it today, and then go into Matlab and show how these things are computed in Matlab. Okay. So once again, we are interested in finding the integral from a to b of this function. Okay. That means find the area under the integral, under the curve, and we are dividing that into n equal intervals. N equal intervals, and so the integration is done in sections, in segments, going from x0 to x2. For example, the first thing, we are just taking these two and finding the area under that curve. Why do we have to take two segments at a time? Because we are putting a quadratic function, not a linear function as we did in the previous case. We are putting a quadratic function. So we're going to take these three data points and fit a quadratic through that by taking the second degree term from the polynomial and then integrate that. And that's why we decide we take two terms. Now, if you want to extend this to three terms, then you will take three segments at a time. Okay, and this can be continued indefinitely, but often we strike a compromise in terms of the truncation errors. And Simpson's rule is pretty good. Normally, you don't go beyond that. The two most popular methods are the trapezoidal rule and the Simpson's rule. And the relationship, if you recall from the last time, is x is equal to x0 plus alpha h. So when x is equal to x0, alpha must be 0. When an x is equal to x2, there are two segments, so alpha must be 2, because you're going by 2h. From x0, you go to 2h to reach x2. And it is a second degree polynomial with a reference point x0 and the new function in alpha. So the integration is with respect to alpha. So dx has become, for example, from this one, dx is equal to h d alpha. H is a constant, the step size is a constant, and alpha is a new variable. So that's how we obtained dx, which became h times d alpha. Now, the neglected term in the next series, in general, and this is the point I wanted to drive in the last lecture, we didn't have time. The next neglected term in the series is going to be of order h cube. Okay, so in principle, the Simpson's rule must have a local truncation error of order h to the power 4. Why? Because you have h cube here and you have h there. But it turns out that when you calculate this term explicitly, the coefficient that is appearing in that integral turns out to be 0 automatically. So this is just a coincidence. And so we actually get a formula that is more accurate for a second order method that fits a quadratic polynomial. Okay, so we will see that pretty soon. So the first thing that I'm going to do is take P2 and replace it by the expansion 1 plus alpha delta plus alpha times alpha minus 1 over 2 delta square operating on F0 times h times d alpha. Integral limit is 0 to 2. Okay, alpha is my new variable. And it's a quadratic expression, you can see there. So the next neglected term is actually a cubic term. But the cubic term has a coefficient which is alpha times alpha minus 1 times alpha minus 2. Okay, and also integral is between 0 and 2, and you have h d alpha. And of course, the next term is there. It's an infinite series. So there are subsequent terms. So when you evaluate, for example, f0 times 1 times h, so the h comes out, this h that you have here comes out here. So you have f0 times d alpha. So the integral of d alpha is alpha. The next term is delta f0 and integral of alpha d alpha. Alpha d alpha is alpha square over 2. Okay, so this term comes from there, and this term comes from that, and then the next term, of course, comes from there. Okay, so the third term is 1 over 2 factorial, then alpha square d alpha, which will become alpha cube over 3, minus alpha d alpha, which becomes alpha square over 2, and then of course you have this del square of 0. The limits become 0 to 2. Okay, so typically we would have said, okay, the next neglected term is of order h cubed, so times h, so it's going to be of order h to the power 4. But it is this term, this entire term, when you integrate it, becomes 0. Okay, so what I'm saying there is if you carry out the integral between 0 to 2 of alpha times alpha minus 1 times alpha minus 2 d alpha, that will be exactly 0. Even though the delta square term that multiplies, delta cube term that multiplies is not 0, the coefficient that multiplies that, which is a number, turns out to be 0, that integral. Okay, so you gain accuracy just coincidentally. And so the next non-zero term is only of order h to the power 4, which gets multiplied by h, so it actually becomes h to the power 5. So it's a very high accurate formula for using 3 points. So the gain that you have from going from trapezoidal to Simpson's rule is tremendous. Okay, any questions on that? This you should verify. How can you verify that? Of course, it's a polynomial cubic expression. You can multiply it out, integrate it, and in an exam, that's what you would have to do. But in Matlab, if you want to verify that, how would you do that? I can define, you can use symbolic toolbox. I can do the integration. I can define sims x, for example. I'm defining a symbol. And then I can define my function as equal to x times x minus 1 times x minus 2. So now f is a symbolic expression. That is the integral term that I wanted to evaluate here. Alpha times alpha minus 1 times alpha minus 2. Okay, I'm just calling alpha as x for integration purposes. And then there is a function called int f. Okay, so it calculates analytically. This is exactly what Mathematica will also do for you. Okay? If you want to learn a new language, Mathematica, that's fine, but you can do the same thing within Matlab environment. So define a symbol. So x is not a number anymore, it's a symbol. We define an expression in terms of the symbol, and int is an integration function that takes f and provides the integral of that. You can also evaluate the definite integral of that by putting the limits 0, 2. And it is 0. Okay, so it is so easy to do all these integrations. A lot of the things that you did in the exam, for example, doing the iterations in an exam, it does take time, okay, with the calculator. But in front of a Matlab, you should be able to do that much more effectively. One of the questions was whether the method, the fixed point iteration method, will converge. So you need to take derivative of g prime, and evaluate it at the root. Number of people got that and actually did that. But those things would be piece of cake in the Matlab environment, because all you need to do is define the function, ask it to take the derivative. There is, just like int, there is another function called diff, which takes a differentiation of any function. For example, if you want to take the differentiation of f with respect to x, there it is. Okay, so it's really a very powerful environment. Okay, so that term turns out to be 0. That integral turns out to be 0, and hence we have a local truncation error of order h to the power 5. Now we still need to develop the formula. That means we need to substitute these limits and evaluate those numbers. Okay, and when you do that, you get this formula, which is called the Simpson's rule. And Simpson's rule basically takes 3 functions, f0, f1, f2, and they're all equally spaced. Okay, so it takes the first number f0, then 4 times the second number, and then the third number, and then multiplied by h over 3. That is the area under that curve. Okay, so if we have to apply this globally to repeat from A to B, okay, I divide this into a number of equal intervals. Is there a restriction that you have to place on how many intervals we divide that into? In the trapezoidal rule, you can choose to divide that into 10 or 11 or 12 or 13 or 100 or 101, whatever you want. N can be any number that you fix. But in the Simpson's rule, my question to you is, understanding what Simpson's rule is, it's simply you take 3 successive data points at a time and then put a quadratic through that and plug the formula numbers into this formula, and you get the area under this. Then you take the next 3 and do the same thing. Okay, now this becomes f0, f1, f2 if you like, and plug it into it, and you will get a it needs to be an odd number. Okay, so that you are not left with, for example, the way that I have it will work. Okay, so the next one is going to be like this, and the next one is going to be like this. But if I had one extra additional piece, then I cannot use the Simpson's method for that piece. I need to use the trapezoidal rule for that particular piece, and then I can add them all up. Okay, do you understand? The restriction in the Simpson's rule is that it must be an odd number, so that you can take a pair at a time, 2 strips at a time, and then apply the formula repeatedly. And when you do that, you will find that the middle one, okay, if I label them, for example, as 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm starting from 0 to 8, so I actually have 9 data points there. So the first one appears only once, okay, and the last one will also appear only once. But the ones that are, for example, odd will be multiplied by the coefficient 4, because those are the ones in the middle. And the ones that are shared by 2 successive strips will be multiplied by 2. Why 2? Because you are including the ones from the left side. So you are evaluating this integral. You will have f0 plus 4 f1 plus f2. When you are evaluating this one, you will have f2 plus 4 f3 plus f4. So f2 appears twice, one on the left side, one on the right side. Okay? So when you are adding them all up, the Simpson's formula is typically written like this. The first point, and then 4 times all the odd points in between, and twice all the even points, and then the last one. And that will have a truncation error of order h to the power 4. That is a global truncation error, because you are adding all the errors in every pair of steps. Okay. Now, as I said, if you don't divide that into an odd number of points, if you have an even number of points, you will be left with the last one. I said you can use the trapezoidal rule. But what would happen to the errors? Trapezoidal rule has an error of its cube, right? So this one has an error of h to the power 5. So think of h as being 0.1. So the trapezoidal rule will have an error of 0.001. So in the third decimal place, the trapezoidal rule will give you an error. Okay, whereas the Simpson rule will give you an error in the 5th decimal place, 0.00001. Okay, and hence when you are adding some sections from trapezoidal rule and some sections from Simpson's rule, the total result error would be what? Are you following my question? I'm trying to point out the dangers in mixing 2 different formulas. Okay, this is also true in numerical differentiation. It is also true in numerical integration. If I choose to use Simpson's rule for some sections of the range from A to B, and another section I use trapezoidal rule, the trapezoidal rule will have a larger error. It will have less significant digits in terms of accuracy. If I add that to the Simpson's rule, which has more accuracy, the total result will be corrupted by the errors that are in the trapezoidal rule. So it is never a good idea to mix 2 different formulas. So when you're designing your scheme, you should always make sure, or when you're designing your experiments to take data, if you're going to use Simpson's rule, make sure that you plan it in such a way that you have an odd number of data points. Okay? Any questions? Okay, I'm going to do a few examples now. Okay, in Matlab, illustrating the tools that are available for numerical differentiation and numerical integration. Okay, so let's take this expression e to the power minus x sine 2x minus 2. Okay, so I think I've already defined sims as x, and then I'm going to define my function as, I need to switch between these two, e to the power minus x times sine 2x minus 2. Okay, one of the things I guess that came out from the midterm exam, whenever I have these sine functions, normally the calculations are done in terms of radians. X should have the meaning of radians. So if you set your calculator to do the calculations in degrees, the numbers will be in error. Okay, but I was not going to penalize, but I might have penalized because I was just checking the numbers. Well, this is for the second question. So if any of you think that you made an error in degrees and radians, and that's the only error that you made, after I post the solution, compare it. And if that's the only error that you made, and I've taken marks for that, you can come back to me and I will give it back to you. Okay, I'm not going to penalize you for that. It is an error. It is a real error. If you go into industry and solving problems in those, you could get wrong numbers. Okay, but in here we are just checking concepts. So I was checking whether you know the difference between the secant method and the regular false-side method. So if the procedures are right and the numbers are wrong, I think I might have taken 2 points out. So if that is the case, and if that's the only error you made, you're welcome to bring it back to me and I will take a look at it. That is after you come back from after you do the assignment, next assignment. I want you to do the next assignment. And then I'll post a solution and then we can make these corrections. So here I have defined a function and I want to find the integral of that function between the limits 0 to 2. What are the tools that are available? Okay, the one I already told you is symbolic integration, which is int f comma 0 comma 2. So what has happened? Okay, I asked it to integrate that function f between the limits in 0 and 2. And can you look at that expression and tell me what it has done? It has not given you a number. You were expecting a number, right? It's a definite integral, so you're expecting a number.
But just plug in their values for each.
Exactly. It did integrate the function. It did substitute the upper and lower limits, but it did not evaluate them. Why? Because symbolic processes are very picky. If you have an irrational number, they don't automatically convert it into a finite floating point number. So this is actually a number, but a number that you need to calculate, a calculating cos of 2 to infinite number of positions if you want. So there is another built-in tool in both, I think, in Mathematica and Maple. This is actually a subset of Maple. Matlab has made an arrangement for Maple to include the symbolic tools. So there is something called VPA. VPA stands for Variable Precision Arithmetic. Okay, so it actually takes any numbers and calculates them, converts them into floating point representations, converts them into numbers. Okay, so I can put ants there. So it takes that answer, evaluates them to any precision that you want. Okay, so by default it prints them to maybe 20, 30 digits, but you can always go and say, do this for 100 digits. There you see. Right? So the variable precision arithmetic actually uses an algorithm because in hardware, all these computers can use only 8 bits per number. That gives you about 16 significant digits. That's what Matlab does as well. Okay, but in software, you can actually calculate this to any precision that you want. Okay, and so VPA is the one that allows you to convert a symbolic expression in numbers into floating point numbers. Okay, so this is the answer. This is the exact answer to that many significant digits. Okay, whether 100 digits or 24 digits. Now what we are going to do is calculate that numerically using trapezoidal rule, using Simpson's rule. What are the tools that are available in Matlab that will allow us to do that? Okay. So when I say we have to evaluate it numerically, that means I need tables. I need numbers. I need F0, F1, F2, F3. So I need to be able to generate those numbers. Okay. So I'm going to write a small function. And that function is going to calculate x values and return the function values. Okay. A equals f and x. Okay, and f is equal to exponential of, once again I forget, minus x dot star sine of 2x minus 2. And, okay, so this is the function that's going to take whatever x value you give and evaluate the number for that. So let me save that and then test whether it is working or not. Okay, so I'm going to say, what is fn of 0? What is fn of 2? Okay, so now we have a function that can take x and return numbers. So I'm going to create a vector that's xi equal to 0, 0.5, 2. Okay, and then I'm going to evaluate those functions fi equal to fn xi. And let me plot that xi comma fi. Okay, so that is the function. Now this is an approximate representation of the function. Why do I call it approximate representation of the function? What does the actual function look like? Well, there is another graph called easy plot. I don't know whether you have come across this yet. F comma 0 comma 2. So what did I just do? Plotted the function using what?
You use more increments in your step variable.
Right, very good. But did I do that?
No, it's a built-in function.
It's a built-in function called easy plot. So easy plot takes any expression. Now f there is not a numerical function, it's a symbolic function. F is that expression. Okay, so easy plot takes an expression like that and you give it a range 0 to 2 and it decides how many places I need to evaluate it so that I produce a smooth curve. Okay, so the actual curve looks like this, but its approximate representation, which is what I plotted, looks like that. What is the difference between these two? I chose to evaluate it only at 0, 0.5, 1, 1.5, and 2. So when I say evaluate the area under the curve, what am I going to do? I'm going to just draw a line and then take the trapezoidal rule and find the area under that straight line segment, right? Whereas the area under the curve actually should be corresponding to the smooth portion. So if you take, for example, this section, can all of you focus on that from 1 to 1.5 in these two graphs, from 1 to 1.5. And I evaluate the actual integral and I evaluate the numerical approximation. Which one would be higher? Actual one would be higher because I have a curvature that goes like that. I have truncated that. Okay, so in order to get closer to the actual result, that is in order to get more accurate result, what do I need to do? Divide it into more number of points. I just chose to divide between 0, 0.51, 1.52. I have 5 points. I must take maybe 100 points. Okay, then I will see that the accuracy gets better and better. That's one way of improving the accuracy. That's what I want to point out. Okay, so let's go back to Matlab, and there is a function called trapeze, and it takes fi, xi, and I guess it's not returning the right answer, right? Which used to be minus 0.3. What was it? Remember, what we are trying to get, the exact answer is minus 0.3504. From trapezoidal rule, I want to get that answer. So let me just read what trapezoidal requires. Computes the approximation of the integral y with respect to x. So what did I make? What mistake did I make? xi fi. I entered it as fi xi. The integral, the integrand should be the second operand. Okay, so TRAP is it xi fi. It is minus 0.3579. The real answer is minus 0.305. Okay, so how can I improve the accuracy? As I said, you decrease the step size. Remember, the truncation error is what you are trying to control. The truncation error in trapezoidal rule, the local one is of order h cubed, the global one is of order h squared. Since if when h is 0.5, 0.5 squared, 0.25, okay, error is of that order. By simply increasing that to 0.05, for example, and then I calculate the function at those positions. Okay, now I plot this. You can see already that it will be a lot smoother. Okay, this is the plot with step size of 0.05. Now the error is of the order of 0.05 cube, local error. Okay, that's going to be 0.000625 or something like that. And you will see that in the use of the trapezoidal rule. If I use trapezoidal rule on this, it's already 0.3505. And the exact analytical result was 35042. So we are still not there, but the error is in the 4th decimal place. And if you want to get that also, what do? Instead of 0.05 as the step size, you reduce it to 0.01 or 0.001. Okay, so you control the step size in terms of controlling the error. Any questions on that? Okay, so there is a function called int in Matlab that is used for symbolic integration of analytical expressions. There is a function called trapeze, which uses trapezoidal rule, and you control the error by controlling the number of data points that you divide. There is also a function called quad. Okay, quad uses a very sophisticated version of Simpson's rule. So it actually uses something called adaptive quadrature. What that means is it's going to decide where it's going to evaluate the function. So you must give quad a function. You cannot just give a tabular data. If the tabular data is all that you have, then you are limited to using trapezoidal rule in Matlab. Okay? But if you have a function that's a complicated function and you want its integral, then you write that function like we did, and then you can use it with quad. Okay, so if you say quad at fn, 0, 2. Fn is the function that we just wrote. Okay, so it gives you more accurate results. Now, quad will also take you tolerance. You can specify the error criterion. So it will try to meet that by automatically dividing your domain into unequal intervals. So it's a much more sophisticated method of evaluating integrals of functions. Okay. Now, for numerical differentiation, what do we have? There are also, of course, we have what we have seen. We've kind of opened the door for integration, numerical differentiation. When you have a function that's a function of two variables, we have partial derivatives, right? When you have partial derivatives, you are taking the derivative in each one of the individual directions. So all these formulas that we have developed for numerical differentiation will be applicable for ddx or ddy or ddz. The same idea, but in different directions. And you have the same thing for integration. This is a line integral. You can have a surface integral, double integration, or triple integration. Okay, and there are functions in Matlab for double quad and triple quad. Okay, that will handle double and triple integrals. So that basically completes the. Yeah, sorry.
So for double quad and triple quad, those would have to be two variable functions and 3 variable functions respectively.
Yeah, yeah. So what for double quad, for example, it basically means that you have f of x, y, dx, dy from some limits, x1 to x2, y1 to y2, right? Geometrically, what it means is f of xy is going to be a surface. This is x, this is y, this is f. Okay, so you have, when you plot that, you get a surface like that. You are asking what is the volume under that surface. The double integral interpretation is that. Okay, so you need to write a function that will return the function value on the surface for any given value x and y. And then you indicate what are the limits in the x direction and the y direction. And double quad will then construct that surface and apply. How do you evaluate double integrals? You must have seen that in calculus, right?
Inside out.
Right, you do it one time. So you may choose to do the integration in the x direction first, and then take that result and then do the integration in the y direction. Just like partial derivative in one direction at a time. So that's what it will do. It will lay out a grid in the x direction and in the y direction and carry out applying Simpson's rule. For example, along this line, you'll get the integral under that curve. And then you go to the next one and the next one. So from a two-dimensional array, you collapse that into a one-dimensional array with integrals on that. And then you apply the integration one more time. Okay? These concepts, I guess you will probably, if you go to graduate school, you will learn why you need it and how you can do it. But it's basically an extension of this idea that we have seen. Okay? Any other questions? Once again, the point I think is the Matlab is a very, very powerful environment for any of these numerical types of calculations. Here is an example which shows you both numerical differentiation and integration, application of that. I've already talked to you about it. This is typically, you will probably do it in your junior lab or senior lab. You have a reactor. Reactor is just a cylindrical vessel with a stirrer, and you have some feed coming in with certain composition. And some reaction is taking place, and you are monitoring in a batch sense. For example, in this particular experiment, your goal is to find out what is called the rate of reaction. Okay, where is that expression? So the rate of reaction is given by an equation of this form. Have you done physical chemistry yet? Not yet. Some of you have done it. You have seen the rate expressions there, rate of reaction. Yeah. So RA is called the rate of reaction. It simply says how fast the reaction is proceeding. The reaction is between A and B. You have two materials, two chemicals, A and B, that are combining to produce a product or two products, whatever it is. Okay. So in this case, the rate depends on the concentration of Ca and the concentration of Cb. So you call this as a second order reaction, for example. Two molecules have come together to form a product. And experimentally, what I can measure is simply this data. As a function of time, I pour A and B, and I wait for 1 hour, and I sample it, and I see how much of concentration of Ca is there in the reactor. I wait for another hour, and I measure the next concentration, And what I get is a data that it's like this, Ca as a function of time. Okay, and similarly, Cb also will decrease because Ca and Cb are being consumed and a product C and D are being produced. So from this data, I propose a model. So this is, if I go to the lab, this is the experiment I can do, and this is the data I can get. Time as a function of Ca, and once I have Ca, using stoichiometry, I can find out what Cb is. There is an equation. If you tell me what Ca is, from, for example, Ca naught, initial concentration, certain amount has reacted. So an equivalent amount must have reacted with B, because every mole of A reacts with 1 mole of B. So you start with what is your initial composition in B and subtract that out. So if you know Ca, you know Cb, because they're both being consumed at the same rate. Okay, and that comes from an understanding of the chemistry of the process. But for our purposes, if I measure this, I can easily calculate what Cb is. I have a formula. But I need to know what the initial concentrations of Ca and Cb are, the amount that I'm pouring into the reactor initially at time t equal to 0. From that, I can construct a table of Ca, I construct a table of Tb. But my goal as a chemical process engineer is to estimate what this rate constant is. Okay, so I have information on Ca, I have information on Cb, and I have a model. So I need to calculate this K. Why would I need to calculate this K? Because I do this experiment and I find out how fast the reactions are proceeding. Then I can take that K and I can build a reaction in series, a tank, and another example that we saw earlier. Or I can design a new reactor, plug flow reactor. There are different kinds of reactors. Once I know the reaction mechanism and the rate constant, I can design or I can optimize the performance of an existing reactor. Okay, so in those kinds of problems, I have to calculate what dCA dt is. From an experiment, I cannot get it. From an experiment, all I can get is how Ca changes with time. So I need to be given this table of data. I need to be able to calculate what the slope is. How does the slope change? The slope keeps decreasing at various times. Okay, so that slope is nothing but dCA dt. So if I can calculate that, then the only unknown in the equation would be K, I can calculate k. And once I have that, I'm ready for the design part of the problem. Okay, that's the reason why I need to know how to take numerical differentiation and numerical integration. Now, there are several parts to this problem. I'm going to talk about only a few and leave the others for you to think about. Okay, so the first part of the problem, do you understand the problem? Any questions on that? No? Okay. So the first part of the problem is estimate the values of the rate constant k by evaluating the derivatives at t equal to 3, 5, and 7 using the 3-point central difference approximation. So I've kind of given you all the information that you need. At these times, time equal to 3, 5, and 7, calculate what the k value will be. Remember, the k value should actually be a single constant. But because of errors in the numerical, in the experimental data, and in the numerical evaluation of the derivative, we will find different values for k depending on where we evaluate the slope. Okay, so if we evaluate the slope at this point, we might get one value for k. If you get it here, you might get a different value of k. So we can take all these values of k and then do a statistical analysis. What is the mean? What is the spread? And that will tell us a little bit about what are the errors in the data itself. Okay, or you can do a least squares curve fitting. So everything that we've seen so far in functional approximation comes in handy to apply to this particular problem. So the first part, let's think about it. How will you do that? Let me try to shrink this a bit. Okay. So the question is, at t equal to 3, 5, 7, using 3-point central difference approximation, evaluate the rate constant. How many of you think you can do it? You know how to do that? I have to tell you what the central point approximation is. So in an exam, what you will have is this table. So from this table, you need to pick what is the right formula. So let's go through that exercise first and make sure that everybody can do it. What formula would you pick to answer that question? What is the 3-point central difference formula that gives you the first derivative? The third one? Is that what you mean? Okay. How many of you agree with that? Let's examine that. What is a central difference formula? Okay, you saw your folly there. Okay, the central difference formula will say that I will take the central point and the point ahead and the point behind. So if I have I must have I plus 1 and I minus 1. Okay, it must be centrally located. The 3 data points must be centrally located. Okay, so if you go back to the table at, for example, 3, the first thing, let's do it at 3. Okay, so I'm going to use 3 and I'm going to use the point behind and I'm going to use the point ahead. Okay, so which one? Fifth one? How many of you agree with that one?
Yeah, but where's FI? Don't you have to have FI too?
Good question. The formula here need not have all the data points. In this case, you can think of it as having a constant times fi plus 1, a constant times fi plus constant times fi minus 1. And the constant with fi turns out to be 0 in this particular formula. Okay, so we are using the point ahead and behind, but we are not. This formula does not have the point at fi itself, but you don't need it. If the formula doesn't ask for it, you don't need it. What is important for you to recognize is that it is the first derivative. It is the first derivative at xi at the current point. The first derivative at xi is given by the function value at I plus 1 and the function value at I minus 1. It doesn't have to have all the numbers spanning that. Okay, divided by 2h. And what is the truncation error here? Is of order h squared. That's a good formula to use. Okay, so that's a formula that we are going to use, but 3 times at 3 different locations. Any questions on that?
Which one would be backwards?
There are 2 backward formula. Can you identify? You're asking me and I'm asking you back to think about. I can point it out, but I want you to go through the thought process of how do you identify a backward difference formula. The backward formula would be I with I minus 1 behind. Okay, and that would be one backward difference formula, which is first order, and the second one would be this one with I minus 1, I minus 2. Okay, where would you use that? Now that you raised the question, where could you use a backward formula in that table? At 8. Because here you cannot use the central difference of forward difference because you don't have data point there. But if you want to calculate the K value at this location, you must use either the first order backward difference or the second order backward difference. The same thing at the very top. If you're calculating the slope at the first data point, you can use only the forward difference. Okay? Good questions. Any other questions? Okay. So I know the formula now. So how would I solve this problem? dCA dt at t equal to 3. What would that be?
F is equal to 0.1234. F2 is equal to 0.1651. F4 is equal to 0.0.
You just use 4 and 2.
Yeah, all you'll have to do is, this is, if you call it F4, F3, F2, so it's going to be F4 minus F2. Okay, so it's going to be 0.0960 minus 0.1651 divided by what? 2h. Divided by 2, you have to look at the formula, it's 2h, so it'll be 2 times 1, h is 1 in this case. Okay, so that will be the estimate of what the derivative is, one of the estimates for what the derivative is, but it is second order accurate. Its error is of order h squared. Okay, and this actually is not a very good table because normally you will have the step size is less than 1 so that the truncation error becomes smaller and smaller. Okay, as you take more higher order terms. You get the idea. Now you can do the thing for t equal to 5 and 7. So when you have t equal to 5, we're going to use this and this and this to calculate what the derivative is. Once you have the derivative, whatever that number is, then you can plug that into this equation to calculate what k is, because k is now going to be equal to minus dCA dt in the numerator divided by CA times CB. We have just calculated what the numerator is. We figured out how to calculate the numerator. What is the denominator? CA times CB. Well, CA is the number that is given. Which number would that be for this case? 0.1234. That is the concentration at that particular time, the reference time. Okay, so it's going to be 0.1234. What about CB? CB you calculate from this formula by putting CA equals 0.1234. Okay, so you know all the numbers on the right hand side that will give you an estimate of what K is. Okay, so we used numerical differentiation to get that particular value of K. But the problem is, if I choose a different formula, a forward difference or a backward difference, at the same point, I can do that. Can I do that? For the same 0.3, if I use a forward difference, what would I do? I would use this, this, and this. And I will get a different estimate for the derivative, the same derivative. Will the numbers be exactly the same? No, they will be different. Okay, so I'll get different estimates for K. And then I need to kind of take an average of that for K. So there are better methods of doing it, but I'm trying to illustrate how you would use numerical differentiation to get estimates for K. Let's go to Matlab and use the simpler idea and use some of the tools there to solve the same problem. Okay, and this is the one that I'm not going to do, but I'm going to ask you to look it up because this illustrates how to use numerical integration. Using a trapezoidal rule or Simpson's rule, you will calculate this integral, you know the time, and the only unknown, and you know CA naught, CB naught, so the only unknown will be K that you will solve for. That will be called an integral method. You will see both methods in the rate method and the integral method in the reactive design course. Okay, and the integral method always will give you more accurate K values. Why? because integration smooths out the errors. Differentiation amplifies the errors. So if you calculate k from differential methods, you will have a larger error. Okay, so let me take the second problem, which says then evaluate the slope at every data point using a suitable order finite difference approximation. So I say you make the decision. Whatever order that you think is good, use that, and then do a least squares curve fit on that. Okay. Let's go to Matlab and see how we would calculate the derivatives in Matlab. Okay, I showed you how to do it by hand. I have the data. In fact, I have more than the data that I need. Okay, so I have the data stored in an Excel spreadsheet, and I'm going to, of course, here I have done the calculation in Excel itself, but I'm going to export it to Matlab, that data. So in Matlab, I have a variable called data, and it has time in the first column, CA in the second column, and CB in the third column. Let me actually load them in the variable called time. CA equals and CB equals. Okay, so I have three variables, T, CA, and CB. Okay, and I wanted to calculate the derivative of CA with respect to time. Okay, there is a function called diff. Now, diff is the same function that differentiates the data numerically as well as analytically. Okay, so that it determines by examining the type of data that you input to it. It's the same function name, but if I pass to it the vector CA, it's going to give me a set of numbers. And I'm going to ask you to interpret that. So let me ask for help diff. And okay, can you tell me what did that do? Diff CA. I pass the array CA, which has a concentration of CA at various times. When I pass that to diff, it returns some numbers to me. Your job is to determine or interpret what the numbers are by understanding this help message. Pardon me? You can say it calculates the slope, but the slope information will require both the y-axis and the x-axis difference, right? These data are all uniformly spaced on the x-axis, which is the time for us. So it simply takes a difference in the y-axis variable, that is CA. So it tells you diff for a vector of x is x2 minus x1, x3 minus x2, etc. What is that? The first number that you get here, this number 0.0811, is CA2 minus CA1. The second number that you get here is CA3 minus CA2. The third number is CA4 minus CA3, etc. Okay. So what would that numbers, what would you call those numbers in the terminology that we have seen? If you say it would be forward difference, you'd be right. If somebody says it's backward difference, you'd also be right. Why? Forward difference means I'm taking this with respect to the first reference point. Okay. Backward difference means I'm taking that with respect to the second reference point. Okay. So how many numbers will there be in this? One less than what is in CA. Okay. CA has 9 numbers, and this answer, I guess I should actually store it, has, let me try to shrink it. Okay. So CA is 9 by 1. So there are 9 numbers in CA, and the answer has 8 numbers. These are the differences between the 9 numbers. Okay, so there's one less than that. Okay, so that's how you calculate difference tables in Matlab. Okay, so if I say, for example, del CA equals DIFF CA. Okay, that's the first difference. If I say del 2 CA, I want to take the second difference. All I have to say is this 2. How many numbers will I have now? 7. This is the second column in the difference table. Remember, a few lectures ago we constructed the difference table. The first column was simply the difference between these two numbers. The second one was the difference between the first differences. Third one is the difference between the second differences. And Matlab has a function called diff that does this calculation for you automatically. Finite differences of any order. So the order number is the second parameter that you give here. Okay. In this particular problem, we don't need the second difference, but I'm just showing you that it can calculate finite differences of any order, and you can interpret them either as forward difference or as backward difference. That depends on your reference point position. So all we need is the first difference, del CA. Okay. So let me go back and maybe indicate what we have done here. So here we have TI CA 0, 1 all the way to 8. Let me call it CA 0, CA 1. These are numbers. Okay. CA 8. And we have delta CA. That is the difference between these. Okay. And that I have stored in the variable called del CA. Okay. And what I want to do is divide that by delta t. In our case, delta t happens to be 1. So that is actually a measure of the derivative. Okay. And so I have obtained the left-hand side. Okay. And I need to get what the right-hand sides are for each one of those variables, and I can divide left side by right-hand side, and I get the value for k. Okay. So all I need to do is apply in a vector form. But the point I wanted to make is on the right-hand side, I will have 9 data points for CA. On the left-hand side for the derivative, I have only 8, right? So if I choose to interpret this as the reference point, then what I need to do is I need to take the data points from 0 to 7. Okay. Then what I will have is I will have here a data which will be the derivative approximation for the forward difference at this point. Okay. So I can create a column, but with only 8 numbers that will have the derivative estimates for dCA dt at time 0, time 1, all the way to time 7. Okay, are you following me? If not, please ask. Okay, so del CA, del CA. Okay, 2, 4, 6, 8. So there are 8 numbers, but these are the difference approximations for the first 8 points. That's how I'm going to interpret that. Okay, so I'm going to extract a new vector, CA1 is equal to CA1 colon 7 or 8. Okay, so these are the time, from time 0 to time 7. These are the concentrations. Okay, and I need to do the same thing for CB. CB1 equals CB 1 to 8. Okay, I have constructed all the data I need. I want you to complete the process. How do I calculate K now? It's simply this formula that you need to use. The numerator is del CA, which is the differences, and the denominator is CA and CB. Okay, so to calculate all the K values from all of them, K is equal to del CA divided by CA1 times CB1. Will that work? That's what I wanted to see. You would catch, because each one is a vector, right? So I need to say this is dot, element by element multiplication between CA and CB. And once you get a vector, resultant vector, it's an element by element division, dot. Those are the K values. So you can see that K values are kind of clustered. They should ideally be all the same. there are no sources of error from experiment or from the numerical differentiation, these numbers should all be the same. If the model for that is also right. So there are several ifs. Okay, but it's a good model because they're all clustered around 0.45 to 0.5. That's your rate constant. Of course, it's a minus sign. The reason for that is I missed a minus here. It's minus dCA dt. Okay, so those are the k values. Okay. Any questions? That was the second part of the question. Then evaluate the slope at every data point using suitable finite order difference and evaluate the k values. Now the last one it says is do a least squares fit. What does that mean? That is, find the best estimate of k using a least squares curve fitting.
Error function.
Error function? I can plot, for example, in this equation, the left-hand side against the right-hand side. Okay, let's do that. Okay, so let me create a vector called left-hand side. Left-hand side is minus del CA. That's what I have on the left-hand side. The right-hand side is CA1 dot star CA2. You agree? Oops. C, B. The k is there, but k is the unknown right now. So I'm just treating this as a equation y equals mx plus c. Okay, y is my left-hand side, x is my right-hand side variable, which is CA times CB1, and k is the slope, if you like. So what I'm trying to illustrate is what do we mean by a least squares fit? If I say plot the left-hand side, what do I want? Right-hand side, comma left-hand side. Okay. What would you expect? What am I plotting on the x-axis here? Right-hand side, the product of CA and CB. And there are 8 data points that I have. On the y-axis, I'm plotting the dCA dt. The slope of this should be what? Okay. That's what we mean by do a least squares fit, meaning put the best straight line that you can possibly through that and get the slope. Okay, and that will give you a more smoothed out average value of the k than all the 8 values of k that we have seen. Okay, so how would I do the least squares fit? So I've determined what the right hand side is, determined what the left hand side is. The equation I want to put is something like, for this case, y is equal to mx plus c, but y is my left hand side, which is dCA dt, and x is my right hand side, which is CA times CB, the product. So m is the same as k, the slope that I want to get. So I want to find these two polynomial coefficients, m and c. The question to you is, what tool would I use of the tools that we have seen so far? You don't remember it? Pardon me?
Integration or use traps.
Why would traps be useful here? Remember, what I have is a set of data points that I have plotted, and on the y-axis it is dCA dt, on the x-axis it is CA times CB, and the slope is k. If it were a perfect straight line, I would get a nice k value. Okay, so the least square fit means when you have a set of data like that, relating the left-hand side to the right-hand side, and the expression is by a polynomial, either of degree 1 or degree 2 or degree 3, you are going to try to fit that polynomial. You are trying to find the values, best values for those coefficients, so that the result between what the straight line predicts and what the actual data is minimized. The error is minimized. Least squares minimization concept is what I'm trying to jog from your memory. Okay, so in that graph, I am plotting minus dCA dt, and here I am plotting CA times CB, and the relationship between them is minus dCA dt is equal to k times CA CB, and I'm saying I'm going to write this as y is equal to, let's write it as kx plus some constant v. Okay, so I have a set of data points. They are not nicely falling on a straight line, but I'm going to put a straight line through that. So I'm going to take these vertical distances as my errors, and I'm going to minimize those errors. That's what least square does. Okay, and the function that we have seen that does it is polyfit. It fits a polynomial of any degree to a given set of data point. Okay. So what I need to do at this stage is polyfit. I need to identify that. Did I type? Thank you. Polyfit. What would be the first argument? Right hand side, left hand side. And I need to specify the degree of the polynomial as the third parameter. It will be 1 in this case because it's a linear polynomial. So what does this say? The best polynomial fit that you can put through this data point is as a coefficient of 0.4728. That is our k. And it says there is another coefficient also, the intercept. Ideally, the intercept should be 0. Okay. In this case, it's 0.0013. But I would say of all the estimates that we have made for k values, this is probably the best estimate that we can get because it's a least squares. So it minimizes the error. But the error is coming from taking the derivative on the left-hand side, as well as any experimental error in the data, in the tabulated data itself. Okay. So that basically concludes the functional approximation chapter. We have seen a lot of ideas in here. The idea of a basis function, the idea of polyfit, polynomial curve fitting, how to convert the problem into a system of algebraic equations, and then the least squares curve fitting on top of that, and then the Newton polynomial for equally spaced data. From that, we went to develop numerical differentiation and numerical integration. So this problem tries to bring all of them together and try to complete that problem on your own. And in the next lecture, when you come back, we'll start looking at differential equations. Okay? Have a good break, and the assignment is due today before you go on the break.